So welcome. In the previous class, we have seen how we calculate terminal settling velocities of single particles in an infinite medium. Now let's go to a bed of particles. Before we do that, let's try looking at how we calculate the just to quickly revise. How do we calculate? This is where we are on topic number 5. What is an expression that relates CD to REP for a spherical particle? Derive an expression for terminal settling velocity for Archimedes number less than 18. Derive an expression for terminal settling velocity when the Archimedes number is greater than 3 into 10 raised to 5. Next is, how do we find terminal settling velocity if Archimedes number is in between 18 and 3 into 10 raised to 5? And what is the advantage of using Archimedes number? So these are some of the dimensionless numbers that we have seen so far. What are the dimensionless numbers we have seen so far? Can you list right from first lecture what dimensionless numbers we have seen? And what is the advantage of using all these dimensionless numbers? So chemical engineers will work with dimensionless numbers, the advantage being they help us to calculate across different spectrums, across different situations. Let me just mention some of the dimensionless numbers that we have seen right from first lecture. Friction factor, Reynolds number, roughness parameter, can you think of some more? Head loss coefficient, resistance coefficient, discharge coefficients of Venturi, orifice, control valves. Some more? Head number for centrifugal pumps, flow number, power number. Now, drag coefficient, lift coefficient, Archimedes number. More than 10, 11, more than 10 dimensionless numbers we have seen. The advantage is that you can use this for any situation. Drag coefficient versus RE relationship, that is valid for a solid sphere floating in settling in liquid. It is equally valid for bubble, small bubbles, of course, small bubbles rising in water. It is valid for raindrops. It is valid for droplets coming out of person spreading virus and this and that. That's the advantage of using dimensionless numbers. That's why we try to think everything in terms of dimensionless numbers. Okay, let's go forward now. Imagine that there is a bed of particles. You see, this is a bed of particles. Now, let's say capital T is the bed diameter, the diameter of this column of this bed. L is the length of the packed section. Right? This bed could be vertical, it could be horizontal. Now, when flow is happening, let's say from bottom to top in this particular case, this flow has to go around these particles. So these particles may be uniformly sized, like here, or they may be irregular. Right now, what we are going to say that all particles are of the same size, uniform size of the particle, and each particle has a diameter dp. We are going to define different things. First thing that we are going to define is bed voidage, means how much is the void volume between these particles which is allowable, which is allowed, or which is available for that liquid to flow. That's called as a bed voidage. Okay? It is the volume. If you take a volume like this, it is the volume of the voids divided by the total volume, and obviously the fraction of the volume occupied by solids right? Solid fraction would be 1 minus epsilon. This would be solid fraction. How much of the area, how much of the volume is occupied by the actual solid particles. It is not available for liquid to flow. What is available for the liquid to flow is the voidage. The void means the gaps between these particles. That is what is allowed or available for this liquid to flow, voidage. We are going to find two kinds of velocities. One is the superficial velocity. Superficial velocity would mean flow rate divided by the cross-sectional area, total cross-sectional area. Whereas we are going to define actual velocity between the particles. So you see, entire area is available for the liquid to flow when we say it is the superficial velocity. It is empty cross-section. But when the fluid is flowing through these volumes, these gaps, less area is available. So velocity is larger in between the gaps between these particles. And we call this as actual velocity. And this actual velocity is the superficial velocity divided by this epsilon. Okay. So get these things clarified for yourself. Then only we'll go forward. Okay, now we apply Bernoulli's equation between 1 and 2, either vertically or horizontally. What can we say? If I say vertically, H1 minus H2 is very small as compared to HF, then, or horizontally H1 and H2 cancel each other out. Vertically there is a term H1 and H2, there is a term remaining. But if I say H1 and H2, it's only a small packed bed, but frictional head loss is significant or pressure difference is significant. Correspondingly, we can say that head loss coefficient is just the difference in the pressures divided by rho g. And how do I get HF? It is 2f v square L d by g. So the next question is, how do I calculate friction factor for this bed? That will allow me to calculate how much pressure difference I need in order to make liquid go through the bed at a velocity v. Okay, that's what we want to do. So think about this. How do I calculate friction factor for this situation? Think about that. Here is what we do. What do we do when there is a non-spherical cross section? We say equivalent diameter. So what we are going to do is we are going to assume that this fluid flowing around the particles is like fluid flowing through a bed of narrow, straight portioned capillaries or small tubes. Or we say equivalent diameter. How do I define equivalent diameter? Equivalent diameter we define as 4 times flow area multiplied by wetted perimeter. If I multiply both sides by L, numerator and denominator by L, flow area multiplied by L, that would be the volume available for flow. And wetted perimeter, if I multiply by L, that will be the total wetted area. So I can now substitute for volume available. Volume available would be 4. So equivalent diameter would be 4 times volume available. What is the volume available? It is pi by 4 T square L multiplied by voidage epsilon. That's the volume available for flow. Divided by what? Divided by wetted area. What is the wetted area? Wetted area is the area, surface area of all these solid particles, which is the liquid is wetting all these, because liquid is flowing around all these particles. All the external surface area of the particles is wetted by the liquid. So this wetted surface area, how do I write that? Wetted surface area would be number of particles multiplied by surface area of one particle. What is surface area of one particle? Pi into dp square. How do we calculate number of particles? How do we calculate number of particles? Number of particles would be total solid volume. What is the total solid volume? Total volume available, total volume multiplied by 1 minus epsilon, the solid fraction. Pi by 4 t square L is the total volume of the bed multiplied by 1 minus epsilon is the solid volume. It's volume of all solids put together divided by volume of one particle. That will tell you how many particles are there. Alright. So substitute this here, substitute this here, rearrange all that. You will find that the equivalent diameter is 2 by 3 epsilon dp 1 minus epsilon. So if voidage is more, equivalent diameter is more. If particle size is more, equivalent diameter is more. If solid fraction is more, equivalent diameter is less. Now, so we are saying that this bed is equivalent to flow through these circular tubes of size DEQ. And if the flow is laminar, what is the expression? Delta P is 32 mu V L by D equivalent square. Substitute this here, rearrange what you will find, and then put this V as VL superficial divided by epsilon voidage. Why? Because superficial is easy. Total flow rate divided by total cross sectional area. That's how it is easy to calculate. So then you will find delta P by L is 72 mu VL 1 minus epsilon square dp square divided by dp square divided by epsilon cube. Actually, experimental observed value is, instead of 72, it is 150. Because the flow is not regular, flow is irregular, flow is not in one direction like from here to here. Flow is tortuous. Right? Whereas what L we are measuring is just the physical distance. So to account for all these things, we have to, 72 becomes 150 because 150 is an experimentally observed value. This is called as Pozzeni-Karman expression. You might have heard about Darcy law. It is the same here. Delta P is proportional to some constant or proportional to liquid velocity. And there is a proportionality constant, all this K, called as permeability. You remember that? Darcy law, you might have heard about that somewhere. Permeability of the soil or permeability of the solids. That's how it is defined. Let's just take a quick example. If particle diameter is 0.5 millimeters, rho L is 1000 kg per meter cube, mu L is 0.001, epsilon is 0.6. Put that here. VL is 3 millimeters per second, L is 10 meters. Calculate delta P. Delta P would be 1333 Newton per meter square per meter, or delta P would be 13,333 Newton per meter square. How do you know laminar is valid? Calculate Reynolds number. Reynolds number is 1.5. So almost valid. So it is very small. Okay. Imagine the other extreme. If the flow is turbulent in this equivalent sort of a scenario, how do we get? 2f v square rho L by d equivalent. And f, how do we get? F is practically a constant number, because friction factor versus Reynolds number we have seen. At higher Reynolds number it is practically a constant number. Experimentally observed value is 1.75 rho VL square 1 minus epsilon divided by dp divided by epsilon cube. So substitute for d equivalent and substitute for v square in terms of VL square. So V square would be VL square divided by voidage square. Okay. Substitute that, simplify. You will get an expression like this. This will be an expression. What if it is in between? So then this first of all, this one is called as a Blake-Plummer equation. And this person, Ergun, he just said, oh, if it is overall, if it is somewhere in between, you could just add them all up, and this equation is called as Ergun equation. We use this for whenever there is a flow of fluid through bed of particles, like a column, like a filter cake, and all kinds of situations where we come across. You will see all those situations as we come across. Just to show you, give you some example that really writing these two is valid. So if you say, take this example, if dp is 0.5, if you take this example, you find out rep is 1.5. Delta P from the first term is 13,333. We've seen that in the previous example. And delta P from this part is 583. So if Reynolds number is small, the second term becomes very small as compared to the first term. If you take a slightly larger particle, different density, viscosity, all those things you adjust, velocity you adjust, so that REP is say 50. Then you will find that delta P from the first term is 444, delta P calculated from the second term is 648. Both are comparable. Total is 1092. If you take still larger particles, like grains, if you are trying to dry grains, so sometimes when we want to dry grains, these grains could be really big, 25 millimeters or so, 2 centimeters, and these grains, they could be dried using hot air. So hot air is made to flow through this bed of grains. So that is the situation. Let's say it's a liquid, for example, or a gas. VL is 10 centimeters per second. Reynolds number would be 2500, and delta P would be 177 from the first part, 5185 from the second part. So adding this is okay. It's okay if the particles are small. First term is dominating, second term is not important. Whether we add or we don't add, it's okay. If the particles are large, Reynolds number is large, second term is dominant. Whether we add first term or we don't add first term, it's okay. And in between, just add them both together. Okay, that's an Ergun equation. So you do all these calculations for yourself. Make sure that you get these answers. Don't go forward beyond these answers. Don't go unless you get these answers for yourself. Okay. Now imagine that this is a bed of particles. What are we doing? Imagine that it is a bed of particles. Now liquid is flowing through this bed. Right? Liquid is flowing in the gap between these particles. I've drawn a regular bed of particles as if the particles are arranged in a sort of a nice lattice, but that doesn't happen. See, the particles are arranged how they are arranged. They are not nicely arranged like this. Was just a schematic. Okay, can we write force balance on each of these particles? What is the force balance we can write? Gravitational force. Particles are heavier. Gravitational force downwards. Buoyancy force upwards. Drag force upward. Liquid is flowing around the particle. Drag force is in the direction of the fluid. So gravitational force is downwards. Buoyancy force is upwards. And drag force also is upwards. Now let's write the same thing again when we had the terminal settling velocity. Gravitational force, buoyancy force, drag force. And let's write this for different velocities. Say velocity is 0, no flow through the liquid. Then gravitational force is downwards. Let's say 10. Let's say buoyancy force is 5. Velocity is 0, so drag force is 0. So this 10 minus 5, there is a net 5 Newton downward force. Who's supporting that? Particle is inside the bed, so there is a plate that is supporting these particles. That plate is providing that 5 Newtons of force upward to make that bed rest on that plate. And if you see particles which are at the lower level, these lower level particles are supporting the upper level particles. They are providing the reaction force to make this particle bed stationary. Now I increase the drag force. How do I do that? Increase the velocity. Gravitational force remains same. Buoyancy force remains same. Let's say drag force increases to 1. Now the reaction force provided by the support plate or particle below on the to the particle above is just now 4 newtons. It has reduced. Go further. Let's say this becomes 10, remains 10, this remains 5, this becomes, let's say, 3. Just take some value, don't worry about the actual value. Now the reaction force that is provided is 5 minus 10 minus 5 minus 3, just 2 newtons is supported, given by the support plate. It is given 2 newtons is given by the particle below to the particle above. Increase it further. 10 remains the same, 5 remains the same, this goes up. Suppose it becomes 4.9, 4.99, 4.95, 5. What does that mean? Gravitational force is exactly balanced by buoyancy and drag force. Net force on the particle is 0. Particle is no longer resting. Particle is no longer resting on the particles below. The lowermost particles are no longer resting on the support plate. Support plate is not providing any reaction, as if the particle is just suspended. Force on the particles is 0. Now the drag force is coming from the pressure difference. Drag force is coming from the pressure difference, P1 minus P2. That's how much force is required. That's how much friction is there. That's how much drag is there. So P1 minus P2, P1 minus P2 delta P multiplied by pi by 4 d square, that's the drag force. That must be exactly balanced by the gravity minus buoyancy force. What is the gravity minus buoyancy force? Pi by 4 t square L, that's the total volume, into 1 minus epsilon, that's the solid's volume, multiplied by rho s, gravity force, rho L, buoyancy force. If this condition is satisfied, particle is just suspended. We call this as a condition for minimum fluidization. Why fluidization? You will see in a while. It's a minimum fluidization condition. And this delta P is dependent on velocity, Ergun equation, liquid velocity through the bed, superficial velocity. So as I increase the superficial velocity, as liquid velocity is reached where this condition is satisfied, that's called as minimum fluidization velocity. So if you take the first case, Kozeny-Kármán equation, delta P is given by the first term of Ergun equation. First term of Ergun equation is this. Put that here. Put this expression here. Delta P is 150 mu L VL L 1 minus epsilon square dP square epsilon cube. Put this here and rearrange to get VL. That VL will call as minimum fluidization velocity. You will find this expression. Derive it for yourself. Can I calculate VL by VT, terminal velocity of these particles? How will I get that? From Archimedes equation, from Archimedes number less than 18. VT is dP square delta rho G divided by 18 mu. You will find that VL at the minimum fluidization divided by VT is proportional to epsilon divided by 1 minus epsilon cube divided by 1 minus epsilon. You will find that VL by VMF is less than 1. We'll do a problem as we go along. Second case, if REP is greater than 1, this P should be subscript, small p. If REP is greater than 1, which means second part of Ergun equation is valid, Blake Plummer. The second part of Argyll equation is valid here. Delta P is 1.75 rho L VL square L 1 minus epsilon dP epsilon Q. Put that here. This if you put here, you can get an expression for VL at minimum fluidization. You will find this expression. VL at minimum fluidization. You can calculate VL MF by VT as well, right? Here just take some example. Now, if I increase velocity beyond this value, beyond this minimum fluidization velocity, suppose I make velocity 4, gravity force is same 10, buoyancy force is same 5, drag force now is more, let's say 8. Just some value, don't worry whether it is 4 or 8, 5 or 6 or 7 or 8. It is more than 5, that's what is important. Net force 10 minus 5 minus 8 means minus 3. Minus 3 means upward direction. There is a net force which is upward. Particles will expand from each other. That's why it is called as a fluidized bed. As if the particles behave like a fluid. That's why it is called as a fluidized bed. And if particles go separated from each other, what happens? This is the expression for minimum fluidization in general, right? If particles go away from each other, void age, what happens to void age? Void age increases. If void age increases, delta P again reduces. So anywhere beyond the fluidization, the bed will expand. Beyond the minimum fluidization, bed will expand. Void age will increase till such a time that the pressure drop again balances gravity minus buoyancy force. So if you plot delta P across the bed versus velocity, superficial velocity, you find increase. Argyll equation. Minimum fluidization velocity is reached. Beyond minimum fluidization, bed has expanded. Why it has expanded? Because the drag force is more. Particles get carried upwards. As the particles get carried upward, what does Argyll equation tell us? Void age increases. If void age increases, what does that mean? Epsilon increases. 1 minus epsilon reduces. Delta P tends to reduce. It will reduce to such an extent, or void age will increase to such an extent that the gravity minus buoyancy force is again balanced, and you will find that beyond minimum fluidization, delta P remains the same. That's called as a fluidized bed, and the bed expands. Void age increases till such an extent. Till what extent? Till this expression is again satisfied. So beyond fluidization, we are going to use this expression to calculate the void age. To calculate this epsilon. Then I will know VL, I will know rho L, I will know mu L, I will know everything. I will know dP. I will calculate void age from here. Okay, so this is an example. So consider a bed of particles, resin particles, in fluidized by water. Let's say dP is 1 into 10 raised to minus 3, that is meter, so 1 millimeter. Void age is 0.6. Rho S minus rho L is say 200. Mu L is 0.001. By the way, this should be mu L. Let me just check whether I have made that error here. Yeah, so this should be mu L. Viscosity of the liquid. Let me see if I have done that here. Yeah, oh, sorry. This should be mu L. This is mu L. Okay. Anyway, there is no viscosity of the solid particle, so mu is of the fluid. What is the value of VLMF? VLMF, how do we get? We get from here. We get from this expression. From this expression, if I put epsilon is equal to 0.6, rho S by rho L is this, dP is this, rho L is 30 1000, so rho s minus rho l is there, rho l is 1000, water, mu l is this. I can solve this expression for VL. That's our minimum fluidization velocity. Terminal velocity for this particle, how do we calculate? Calculate Archimedes number first. Check if Archimedes number is less than 18. Check if Archimedes number is greater than 10 raised to 5. If not, do a put the CD expression and solve a nonlinear equation in velocity. Now, if I say that the actual velocity superficial is 2 times the minimum velocity, then what do we know? Then now we know VL, we know mu L, we know dP, we know epsilon. We know mu VL, we know mu L, we know dP, we know rho L, dP, VL. All these things we know. Only unknown we don't know is epsilon, because the bed has expanded. Voidage is more than 0.6 now. We can use the same expression to calculate the value of epsilon. So calculate that for yourself. That's an homework for you. You calculate for yourself. Okay? And check answers with your friends. I am not going to solve it here. Okay. So we have completed. We have come to the end of part 5. We have come to the end of part 5 of the course. Some references for you. We are Fluid Mechanics, White's book. Read chapter 7, section 7.6. That talks about drag and so on and so forth. Drag force arising on particles, ships, birds, and lift force. And you can solve these problems from the book. And related to the terminal settling velocity, related to the packed bed, related to the fluidized bed, there is another book called as Unit Operations of Chemical Engineering by Smith, Harriet, and McCabe. 7th edition. If you see, just happens to be the same chapter, chapter 7. Chapter 7 talks about flow past particles, essentially in single particles or a bed of particles. Okay, so that's what we have completed so far. We have completed the 5th part of our course. Which part of the course? Let's see. Yeah, we have completed the 5th part of the course related to external flows, flow past immersed objects. Okay. So in all these 5 parts, what have we been talking about? We have been talking about forces, we have been talking about energy, we have been talking about velocities of control volumes of particles, of bends, of pipes. We have been talking about macroscopic quantities. Macroscopic quantities, large scale quantities across the whole equipment. We have talked about a pump as a whole. We have talked about pressure drop in the pipeline. We have talked about force on the particle, force on the bend. We have talked about momentum balance for the pump blade, which is a macroscopic quantity. Macroscopic quantity. We have talked about as if our control volume is the whole blade or whole impeller. We have talked about bed as a whole, the pressure drop multiplied by cross-sectional area. That's the net force on the bed as a whole. It's a macroscopic quantity. Those are the things that we have talked about in all these first 5 parts. Now it is time to switch over to microscopic, in the sense that we will look at a differential element and we'll try to look at forces on a differential element, and again look at from a differential point of view, from an infinitesimally small control volume. We will again try to look at forces, we will try to again look at energy, we will try to again look at skin drag and so on and so forth. So essentially 6th part is we are going to do combination of 2, 3, 4, 5 again, but from now a differential, a microscopic, a small infinitesimal control volume, and then trying to look at the whole pipe, try to look at the whole pump, try to look at the whole particle, right? So we are going to go from a microscopic to microscopic. So we are going to look at microscopic first, trying to look at forces, trying to look at energy, trying to look at drag at a microscopic level, at a small level, differential element level, and then we will try to go to the macroscopic level, and we'll get all the things that we have done so far. We'll be able to get from here, from this part. Okay, so that's what we are trying to do. That's what we are going to do now.